with the previous topic, and we must start with topic 4. The heading, topic 4, is stoichiometry. It's just a big word for chemical calculations. Now, when we start off with these calculations, there's a couple of things that you must bear in mind. For example, if I give you a balanced equation, let's just take a simple one. Hydrogen plus oxygen will give us water. Now, from grade 8, 9, we've started balancing equations, all right? Why do we balance equations? Well, I said to you at that point that we cannot create or destroy matter. You can change its form. But if you start with 10 atoms of hydrogen, you must end up with 10 atoms of hydrogen. It can be bonded in a compound, but you can't make the stuff disappear, and you can't make something out of nothing. So when we balance equations, I said to you, we put big numbers in front. So 2 hydrogens, 2 hydrogens, 2 oxygens, 1 oxygen. We will need 2 of those. But now we have 4 hydrogens, so we need to have a 2 in front there. All right. Now, when you look at a balanced equation, you should know that the balancing figure tells you how many of those things you have. So this thing tells me, for example, I have 2 molecules of hydrogen. There is a 1 which we don't normally show. So I have 1 molecule of oxygen, and I will get 2 molecules of water, or two formula units, if you want to put it in that way. Okay, now, when we do chemical calculations, we need to have balanced chemical equations, because now, once we know how to do the calculation, I can say to you, for example, I give you 10 grams of hydrogen, there's enough oxygen in the atmosphere, how much water will I be able to produce? Okay, and you would be able to work that out. So before we then get to doing these calculations, there are a couple of things you need to know. Now, it's a lot of new terminology. There are some new formula. You will have to go through this stuff and keep up with it. Otherwise, it will become very difficult. Now, the first thing, we refer to a quantity as a mole. M-O-L-E. Not a little animal that lives below the ground and eats all the roots. Okay? A mole is a quantity. It's an amount. It's just a very large amount. 6,022 times 10 to the power 23. If I have, you can compare it to, for example, a dozen. If I have a dozen loaves of bread, how many loaves of bread have I got? 12. Okay, so the word dozen tells me I have 12. If I say to you, I have half a dozen, 6. All right, because we know a dozen means 12. Now, in the same way, the mole means 6,022 times 10 to the power 23. It's just a very large amount. So if I have 6,022 times 10 to the power 23 loaves of bread, I have 1 mole of bread. So if I have a mole of water particles, I have so many water particles. That's a very large number. They say this quantity is known as Avogadro's constant. He's just a scientist that worked with us. I'll explain to you where it comes from in a moment. Okay? Why this amount? Now, it took quite a while to get to that point. Okay? Now, Avogadro is the scientist that did this, and they discovered that this number, 6,022 times 10 to the power 23, is exactly the amount of atoms that you could physically count out if you had 12 grams of the isotope carbon-12. So what is 1 mole? 1 mole is the number of particles in 12 grams of carbon-12. But what does that 12 mean on carbon-12? Yes, carbon is element number 6. It has 6 protons. The specific isotope has got 6 protons and 6 neutrons, so it's got a mass number of 12. Okay. Now, 1 proton has a very, very, very tiny mass. All right. So when I refer to the mass of carbon as being 12, Well, you can see it either in terms of literally the mass of the protons and the neutrons, which would be a very tiny amount, or we can just convert it into grams. Okay? Because the ratio of the number of particles would be the same. It's just going to be in a bigger amount. So, Avogadro's constant is if I have the mass number in grams of an element, I have got 6,02 times 10 to the power 23 particles of that element. So if I go and look on the periodic table, let's say phosphorus is element number 15. It has a mass of, let's say, 31. In other words, if I have 31 grams of phosphorus, I will have 6,02 times 10 to the power 23 phosphorus atoms. 12 grams of carbon 12. 12 is the mass number. So if you have the mass number of an element in grams, you will have 1 mole of particles of that element. You have the mass number. What is the mass number of an element? Protons plus the neutrons. If you have the mass number of an element in grams, then you will have 1 mole of those particles. Just for example, calcium. Calcium, because all atoms of different elements differ. Okay? So if calcium has a mass number of 40, if I have 40 grams of calcium, I will have 1 mole of calcium. In other words, I will have 6,02 times 10 to the power 23 calcium atoms. The masses then of all the atoms on the periodic table are measured relative to that of carbon 12, which has been given a mass of 12 atomic mass units, or just simply 12 grams. When they worked out the atomic masses of the elements on the periodic table, it was quite complicated because, for example, if I go and have a look at chlorine, the atomic mass for chlorine is 35.453. So we work with 35.5. It's a rounded off value. But why is it a rounded off value? Because chlorine has got different isotopes. And isotopes occur in a fixed ratio. So when they go and work out the mass of an isotope of an element, or when they go and work out the average mass of one atom, then they go and work out what it would be if I could scoop a bucket and I could work out the average mass of all the chlorines. That would imply the different isotopes as well. Chlorine 34, 35, or 37. They occur in a fixed ratio. And that is why the mass of an atom is not always a whole number. It doesn't mean there's half a proton or half a neutron. It is the average mass of the isotopes of that element. All right, in the first place. And secondly, it is measured relative to that of carbon 12. So if carbon 12 has 12 particles in the nucleus, and it's been given a mass of 12 gram, then hydrogen with 1 particle in the nucleus will have a mass of 1 gram. It's not all that important to understand that, but eventually what we go and do is, when we start working with masses of atoms, we use the relative atomic mass in grams. Because when I have that relative atomic mass in grams, I have 1 mole of that substance. All right, that is a very important concept. Just if we carry on here, what are isotopes? Atoms of the same element having different number of neutrons in the nucleus. In terms of atomic numbers and mass numbers, elements with the same atomic number, same number of protons, but different mass numbers, different numbers of neutrons in the nucleus. The relative atomic mass, just the formal definition, the relative atomic mass is the average mass of the isotopes of an element, all right, of a naturally occurring element, any of the elements on the periodic table, measured relative to 1/12 of the mass of carbon 12, because in carbon 12, if there are 12 protons and neutrons, each proton or neutron has a mass of 1. Okay, which has been given a mass of 12 grams. there's a formula for calculating the relative atomic mass. It's the average mass of the isotopes. For example, chlorine has got chlorine 35, chlorine 36, and chlorine 37. They occur in different ratios. I don't know what they are. But for example, hydrogen, 99% of hydrogen is hydrogen 1. Very tiny amount of hydrogen 2 and 3 exist. So the average mass of hydrogen, if we go and look on the periodic table, is 1.0079. The periodic tables that I handed out to you, they've got rounded off values. When we work with a mass of hydrogen, it has a mass of 1. Okay. If you go to university and you start working on a much higher level, then you would probably work with the unrounded value. Okay. For our purposes, the value on the periodic table, you'll see most of them are whole numbers. Chlorine, for example, is 35.5. One or two of them that have a decimal place. Carbon, for example, has 3 isotopes, carbon 12, carbon 13, and 14. Carbon 12 is the most abundant. All right? Scientists discovered that 12 grams of carbon 12 will contain 1 mole of carbon atoms. 6,02 times 10 to the power 23. It's loads of them. All right? Yes. Well, it gives you an indication of how tiny an atom is. All right. Okay, so this then is 1 mole of carbon atoms. All right, so when you hear the term 1 mole, you must know, okay, mass in grams of the element, mass on from the periodic table, and 6,02 times 10 to the power 23 particles. If I have, going back to my equation of hydrogen reacting with oxygen to give me water, now I know I have 2 moles of hydrogen will react with 1 mole of oxygen, and I will get 2 moles of water, 2 times 6,02 times 10 to the power 23, water particles. Okay, we'll do the calculation in a moment. All right. Now, when you take the relative atomic mass of an element in grams, there will be 1 mole of atoms in that element. If I have a formula unit, let's say I have carbon dioxide, CO2, carbon has a mass of 12, oxygen has a mass of 16, there's 2 of them. Okay, so it's 32 plus 12 gives me 44. If I have 44 grams of carbon dioxide, how many carbon dioxide molecules will I have? 1 mole. 6,02 times 10 to the power 23. Because I've got the relative atomic mass of the formula unit. So now we talk about the formula mass or the molecular mass. If I have that in grams, I have 1 mole of that substance. The amount, 2 moles, ne? Okay, you're starting to get it. All right, so just here's an example. The relative atomic mass for lithium is 7. Okay, it's element number, what, 3? 1, 2, 3. There, 6.941, so it's rounded off as 7. Okay? So, if I have 7 grams of lithium, how many lithium atoms will I have? Avogadro's number 6,02 times 10 to the power 23. AR is relative atomic mass. Okay, A is atomic mass, and the R footnote tells me it's relative. The relative atomic mass of calcium is 40. In other words, if I have 40 grams of calcium, I will have 1 mole of calcium atom. Now, the relative atomic mass of an element is not the same as the nucleon number. I've already said to you why. Who knows why not? Because it's the average mass of the isotopes. When I refer to a nucleon number, for example, if I say carbon 12, then I'm referring to a specific isotope, carbon 12. There is carbon 13 and carbon 14 as well. So when I go and take the relative atomic mass of carbon, then it's 12,011 something or other. We work it rounded off as 12. But that rounded off value is the average mass of carbon 12 plus 13 plus 14. There's just a very little bit of that. That's why it's not a whole number. So, the relative atomic mass, even though it looks like from our periodic table is not the same as the nucleon number. The nucleon number is the number of protons plus neutrons. The relative atomic mass is the mass of all the isotopes of that element, the average mass. It just looks like it is always the same because we work with the rounded off values, but it's not. Now, when we have an equation, or when we have a formula unit, for example, we have water, H2O. Now, water we know is a covalent compound, so we have a molecule of water. In a molecule of water, we have 2 hydrogens, and the relative atomic mass of hydrogen is 1. Oxygen has a relative atomic mass of 16, so the mass then of water that we can calculate using the relative atomic masses will give me a value of 18. Now, we don't have an atom. Can you see that? We have a molecule or a compound. We have a formula unit. So we refer to this 18 as the relative formula mass or molecular mass. If I go and say to you, work out the mass of 1 mole of water, you will use the relative atomic masses, and you will get a value of 18 gram. That would equal the mass of 1 mole of water. So how many water particles would I have if I have 1 mole? If I have 18 grams of water, how many water particles are there? Yes, 6,02 times 10 to the power 23. I'll have 1 mole of water molecules. You following me? How many hydrogen atoms would I have in 1 mole of water molecules? 2 times 6,02 times 10 to the power 23. And how many oxygen atoms would I have? 1 times. You want to have a look at activity 2, page 11, water plus oxygen, a hydrogen plus oxygen, and I get water. Let's balance it. I have 2 over there because I have 2 oxygens over there, so I have 2 oxygens there, but now I have 4 hydrogens here, so I need 2 over here. This is reagents, that is products. Can I create or destroy matter? No. In other words, what I start out with, I must end up with, but it can be in a different form. It can be bonded or whatever. Okay, so let's go and have a look at what we have in terms of the masses. What mass of hydrogen have I got over here? Hydrogen has a mass of 1, but a molecule of hydrogen will have a mass of 2. How many molecules have I got? 2, so I have a mass of 4. Okay? Well, if I have 2 moles, I will have a mass of 4 grams. Are you all with me at that point? Who's not? Oxygen has a mass of 16. How many oxygen atoms have I got? 2, so what mass will I have? 32 grams. So, I have 4 grams of water will react with 32 grams of oxygen. And what have I got over here? Well, that one is 16. Do you agree with me? Okay. Hydrogen has a mass of 1, but we have 2. So it is 2, but we actually have 4. So I have 16 plus 4. Not so. I have 16 plus 2, but how many of them do I have? 2. So what mass in grams have I got here? 32 plus 4. 2 moles of hydrogen has a mass of 4 grams. 1 mole of oxygen has a mass of 32, but to make 2 moles of water, that is what I need. Any balanced chemical equation, if it's balanced correctly, the masses on the left-hand side will equal the masses on the right-hand side, because I cannot create or destroy matter. All right. Let's have a look at activity 1 on page 174. Just sort of take it from one side. Activity 1 says, spend about 5 minutes. Okay, if 1 mole of any substance contains 6,022 times 10 to the power 23 particles. Calculate the number of particles in 7 moles. Well, if 1 mole is equal to 6.022 times 10 to the power 23, then 7 is going to be times 7. Okay, I'm not even going to work out the value. Yes, 4.2154 times 10 to the power 24. The next one, if I have 0.5 moles, I've got half of that, don't I? Then I have 3,011 times 10 to the power 23. 11. Do you follow? Okay, so the last one, if I have 0.25 moles of anything, how many particles have I got? That times that one, a quarter of that. Yes, 1.5055 times 10 to the power 23. Everybody, do you follow me on that? Okay. Now, the next exercise, 2, they go and have a look at the relative atomic masses of the elements given in the table on the previous page. We use that to calculate the relative formula mass of the following compounds. Now, the relative formula mass for a hydrogen molecule, hydrogen has a mass of 1, but how many hydrogen atoms are there? 2. So it will have a mass of 2. Now, when they ask, and this is just a technicality, when they ask for the relative atomic mass or relative molecular mass, the answer does not have units because it's measured relative to that of carbon-12 that has been given a value of 12, just 12 units. But when they ask you to work out the atomic mass or the molecular mass or the formula mass, then the answer must have grams. So this question clearly says work out the relative formula mass. So there are no units to any of those answers. Make a note of that. Okay, the relative atomic or molecular mass or formula mass has no units. Yes, relative has no, because it's measured relative to other thing that's been given a value of so many units. The next one, an oxygen molecule. Now, if you look on your periodic table, oxygen has a mass of 16. We have 2 oxygen atoms. So, oxygen, a molecule of oxygen, the relative atomic mass would be 32. In other words, if I had 32 grams of oxygen molecules, how many molecules would I have? 6,022 times 10 to the power 23. That would be oxygen molecules. But how many oxygen atoms would I have? Times 2. Let's skip methane. Let's go and have a look at glucose. Glucose has a formula of C6H12O6. So, what will the relative molecular or formula mass be of glucose? Well, how many carbons have we got? The relative atomic mass of carbon is 12. Okay? How many hydrogens have we got? 12. The relative atomic mass of hydrogen is 1. And how many oxygen atoms do we have? 6. The relative atomic mass of oxygen is 16. And that will give you a value of 180. So, if I have 180 grams measured out on a balance, then I will have 6,022 times 10 to the power 23 glucose or sugar molecules, yes, particles. If I have 180 grams of glucose, I have 6,022 times 10 to the power 23 glucose molecules. If I asked you what would the mass of hydrogen be in this, it would be 12 out of 180. Okay, in terms of if you want what mass, then it would be 12 grams out of a possible 180 belongs to hydrogen. All right, one more. Let's have a look at ethanoic acid. Formula for ethanoic acid, CH3COOH. Okay, now, What would the relative molecular mass be? Well, carbon has a mass of 12. How many carbons are there? 2 carbons. All right? It doesn't matter that they're not written as C2, okay? How many hydrogens are there? 4. So we have 4 times 1. And the other element that is left is oxygen. How many oxygens are there? 2 times 16. So the relative molecular mass of ethanoic acid, which is vinegar, is going to be 60. So if I had 60 grams of ethanoic acid, I will have 1 mole, which is 6,02 times 10 to the power 23 molecules of this whole thing. Ethanol is an alcohol, and ethanoic acid is a carboxylic acid. Now, empirical formula and molecular formula, lots of new words. Molecular formula, we've been working with it. What is that? Formula for a molecule. For example, H2O is a molecular formula. It's the formula of a molecular substance. Now, we distinguish between something called a molecular formula and an empirical formula. Sometimes we refer to an empirical formula as the simplest formula. For example, look at glucose, C6H12O6. That is not the simplest formula, is it? No. All right? So, when we work with the molecular formula for glucose, it would be that. But when we work with the empirical formula, the word empirical tells you it must be simplified. The empirical formula for glucose is going to be, I'm going to divide by 6, 1, 2, and 1. So there. There are certain examples when we start doing the organic chemistry. If we look at methane and ethane, for example, the molecular formula for methane is CH4. Can I simplify it any further? No. So in this case, the molecular and empirical formula is the same. But now we get a bunch of organic compounds, ethane, propane, butane, pentane, hexane, etc. We have ethane is C2H6. That would be the molecular formula. But what would the empirical formula be? Yes, CH3 in its simplest ratio. Relative atomic mass has no units. That's the value we get from the periodic table. Do they write in their grams? No, because it is the relative atomic masses, and if it's the relative one, there are no units. We use the relative atomic masses to work out the mass of 1 mole of a substance. So then we refer to it, we are working with molecular or atomic masses or formula masses. Then molecular or formula mass is measured in grams. The moment you see the word relative, there are no units. Okay, I'll stop there.